In this video we're going to derive and then apply another method for solving differential equations that are non-homogeneous. In particular, this type of second order linear differential equation with constant coefficients, a y double prime plus by prime plus cy equals g of t, where a, b, and c are constants. So we already know that the homogeneous differential equation a y double prime plus by prime plus cy equals 0 has two solutions, and we're going to write those two solutions in this form: c1 y1 plus c2 y2. What we're going to do in developing this new method is assume that we can find a particular solution of the non-homogeneous dE yp of the form v1 y1 plus v2 y2, where the functions v1 and v2 are to be determined. So let's say to be determined, and the functions y1 and y2 are the same solutions that we have for the homogeneous dE. So on the next blackboard, what we're going to do is take this y sub p, of this structure right here, and take its first derivative and its second derivative and plug it back into this differential equation a y double prime plus by prime plus cy equals g of t. So let's take its derivatives and plug it back in, starting on the next blackboard. So by the product rule, yp prime would equal v1 y1 prime plus v1 prime y1 first times second plus derivative first times second plus v2 y2 prime plus v2 prime y2. Now it turns out when you're solving differential equations, there are theorems that you prove in a more advanced course that say when you find the solution to the differential equation, that solution is unique. And so what we're going to do is make an assumption here that this sum equals 0, and we're going to go through and show that we can find a solution to the differential equation using that assumption, and then we're going to use the theory that says that the solution is unique, so that will justify the validity of making this assumption. So with that assumption, yp prime becomes much simpler. It is just v2 y2 prime plus v2 that assumption that we make back here in this step is that v1 prime y1 plus v2 prime y2, that sum equals 0. So yp prime becomes v1 y1 prime plus v2 y2 prime, and yp double prime becomes, by the product rule, v1 prime y1 prime plus v1 y1 double prime plus v2 prime y2 prime plus v2 y2 double prime. So let's bring all that forward onto the next blackboard. Yp was v1 y1 plus v2 y2, yp prime was, and then let's plug that information into this differential equation that we started with, a y double prime plus by prime plus cy equals g of t. So when we do that, we get a times the v1 y1 double prime plus v1 prime y1 prime plus v2 y2 double prime plus v2 prime y2 prime, and then plus b times the y1 prime, and y1 prime is v1 y1 prime plus v2 y2 prime. And then finally we have c times the original yp v1 y1 plus v2 y2. So what we're going to do, and that all equals g of t. So we're going to do some regrouping here, which is going to allow us to greatly simplify this differential equation that we have here. So let's take all of the terms that have v1 prime multiplying them. So that's that term, I'm sorry, all the terms that have v1 multiplying them. So that's this term, and this term. And so if we write that out, we have this a times, or let's say a times, so let's factor it out the v1. So it's v1 times a y1 double prime plus b y1 prime plus c y1. And now let's factor out, or let's identify all the terms that have that are multiplied by v2. So this term, and this term. So if we factor the v2 out, what's left is v2 times a y2 double prime plus b y2 prime plus c y2, and then the only things that are left are this and this. And so I'm getting a little crowded here. Let me see if I can get this in. So we have all this, and we can simplify this because since y1 is a solution of the homogeneous equation, that means this in parentheses here equals 0. So that whole term is 0, and since y2 is a solution of the homogeneous equation, that in parentheses there equals 0. So we're left with just this. Let's bring that over onto the next blackboard. That's this equation if we divide through by a. And remember earlier we had made the assumption that v1 prime y1 plus v2 prime y2 equals 0. So we've got now a simultaneous set of differential equations which we can solve by the elimination method, by eliminating this first column. If we multiply the top equation by y1, and if we multiply the bottom equation by minus y1 prime. So if we do that, what do we get? So I've identified in the top equation that we're multiplying through by y1, which is in blue, and in the bottom equation we're multiplying through by minus y1 prime, which is also in blue. Also there was a error that I fixed there. Needed to be a prime here and here on the y2. So now if we add up these two equations, we see that we get 0 here, and in the second column we can factor out a v2 prime, and when we do that, what's left is y1 y2 prime minus y2 y1 prime equals y1 times g over a. Let's make note of this factor, or this factor in parentheses here, and notice that if we put y1 here and y2 here, and the derivative of y1 below y1 and the derivative of y2 below y2, and we take what is called the determinant of that, which is the product going this way minus the product going this way. So that is y1 y2 prime minus y1 prime y2, and that has a special name called the Wronskian of Y1 and Y2. So that's what this expression multiplying the V2 prime right here, that is the Wronskian of Y1 and Y2. So putting that onto the, carrying forward on the next blackboard, y2 prime minus y2 prime y1 equaled g times y1 divided by a, and we said that the shorthand name for this is that it is the Wronskian of y1 and y2, so let's divide through by that, and we have v2 prime equals, let's bring the constant a out front, and we've got g y1 divided by the Wronskian of y1 and y2. To solve for v2, we already have a separable differential equation, so we can just integrate both sides of that, and when we do that, we get that v2 equals 1 over a integral g y1 divided by the Wronskian of y1 and y2. If we went back through this and eliminated this second column here, it shouldn't be hard to see that V1 would have a similar structure. It's almost exactly the same. G, guess by what? Not y1 but y2. The Wronskian of y1 and y2 would still be down here in the denominator, and the only difference is that we have a minus sign out here. So here are our formulas for V2 and V1, and those are the functions that we had back here. Right? We said we were going to determine the functions V1 and V2 in putting together yp. So we now have determined those functions, and we now can find yp. Let's apply this to this formula that we've developed to solve this differential equation. We're trying to solve this differential equation. The characteristic equation is r squared plus 1 equals 0, r equals plus or minus I. So y sub h is c1 cosine t plus c2 sine t, and that gives us our y1 and our y2, or allows us to identify them. It also allows us to calculate the Wronskian of y1 and y2, which we set up as this determinant. Cosine goes here, sine goes here, the derivative of cosine is minus sine t, derivative of sine is cosine t, and remember we take this, the product on this diagonal minus the product on this diagonal, and so when we do that calculation we get cosine squared t minus sine squared t, or plus sine squared t, and so the Wronskian in this case is very simple, it's just a constant 1. So V1 is, you recall, minus 1 over a is 1 here, right? So it's minus 1 over 1 The Wronskian is 1, so we don't need a denominator under the integral sign, and it is y2 times g of t. y2 is sine t, and g of t is tangent t. How do we integrate that? Well, let's rewrite it as minus the integral sign is, or tangent sine over cosine, so it's sine squared t divided by cosine t, which we can't integrate in that form, but if we rewrite it as minus sine squared goes to 1 minus cosine squared t, and then it's divided by cosine t. Recall that expression a minus b over c is a over c minus b over c, and so the integral becomes minus 1 over cosine, which is secant of t, and then the second integral minus cosine, right, the first integral is 1 over cosine, and the second integral is cosine squared over cosine with 2 minus signs, so it's plus integral of cosine t dt. The first integral is one that we did a long time ago. You'll look it up in your notes. Ln secant t plus tangent t, and the second integral of cosine t is just sine t. So there is our V1. So let's get our V2. Our V2 is 1 over A, 1 over the Wronskian. Those are both 1. There's not a minus sign out in front of this integral. It is g of t times y1. G of t was tangent t, which is sine t over cosine t, and y1 is cosine t dt. So this integral simplifies without any algebra needed, and we're just integrating sine t dt, which is minus cosine t. So yp is now we're now able to put together yp as v1 y1 plus v2 y2, which is v1 was sine of t minus ln of secant t plus tangent t, and that is all multiplied by y1, which is cosine t, and v2 we just calculated was minus cosine t, and that is multiplied by y2, which is sine t. So let's put the what everything is here. This is the v1, this is the y1, this is the v2, this is the y2, and you can see that the product here, sine times cosine, is going to cancel out this minus cosine times sine, and so all we're left with is this product here. So yp is minus ln secant t plus tangent t multiplied by cosine t. And so let's box that in. Wrapping this up, y is yh plus yp, which is c1 cosine t plus c2 sine t, we already calculated that was yh, minus ln secant t plus tangent t, all multiplied by cosine t. So there is the solution to that. If we consider another differential equation, example 2, where we keep yh the same and just change our right-hand side to secant t, this one we can calculate v1 and v2 a little more quickly, because they turn out to be easier integrals. The Wronskian is the same, the a is the same, so v1 is minus 1 times the integral of secant, which is 1 over cosine t, and remember that y1, right, it's the same y1 right as here, is cosine t, so we're just integrating dt, and so v1 is t. v2 is 1 over secant is still 1, or again we'll write it as 1 over cosine. This time is times y2, which is sine, so we're integrating tangent t, and you'll recall the integral of tangent t is ln of secant t. So we can put together our solution now as, or yp part of the solution, yp is v1 y1, I should have got a minus sign here, so it's minus t cosine t minus t times cosine t plus ln of secant t times sine of t. So here's our yp, which we got much more quickly than we did in our example 1, just because the integrals were easy to do. So there's two examples of the variation of parameters method applied. Let's do just a very quick recap. In this method, we assume that yp can be written in this form. We further assume that we can make the assumption that when we're taking yp's derivative, this part of its first derivative plus this part of its first derivative equals 0. We can do that because of the theory of differential equations. It says if there's a solution, it's unique. We go through the derivation and find out that v1 has this structure, 1 over a g times y2 over the Wronskian of y1 and y2, and v2 has almost the exact same form, 1 over a. The only difference is v2 has a y1, v1 has a y2, and otherwise they're exactly the same, except v1 has a minus sign out front. We applied that to two problems and saw that sometimes those integrals v1 and v2 are very easy, other times it takes a little more work to calculate those two integrals. So that concludes this video on the variation of parameters method.